So we were talking about double integrals. Let me remind you of what we did so far with double integrals. We are learning 3 different ways of thinking about double integrals. All 3 of them are equivalent. The first way that we learned to think about double integrals was in terms of volume. So we started off by first considering functions that were positive and defined on a rectangle. Now, in section 5.2, the next section that we're going to cover, we're going to generalize to domains other than rectangles. For now, we're just talking about rectangles. So under these assumptions, we could define the double integral of f over r to be the volume beneath the graph of f. So for example, this is from an old exam question of mine. Suppose that the US Army issues pup tents that occupy 2 by 1 square meters, 2 meter by 1 meter, okay, of flat ground, of rectangular flat ground. So let's suppose that this rectangle occupies the interval -1, 1 cross 0, 1 in the xy plane, right? That's a 2 meter by 1 meter rectangle. And suppose that the height is given by z equals f of xy equals quantity 1 minus the absolute value of x quantity squared times quantity 1 plus quantity 1 minus y quantity squared quantity n quantity for xy in that rectangle R. So that's the height of the tent. Then you can find the volume contained in the tent if you integrate the function f over the rectangle. As for how to actually perform that integral, you'll have to wait till the end of the lecture to learn the necessary tools. We next generalized our definition to allow functions with negative values by defining the double integral of f to be the signed volume under the graph. So this is where you subtract volume that lies below the xy plane. So that was our first definition of a double integral. The second one, which is equivalent to the first one, used Riemann sums. So let me remind you how those went. First, suppose that we have some rectangle. I'll call it R. And suppose it's the product of the interval AB with the interval CD. And we have some function f of xy, which is defined on R. Then what we do is we divide R into subrectangles. Let's say m of them, let's say mn of them, where we divided the x interval into n subintervals and the y interval into m subintervals. That leaves us with m times n little subrectangles of the original rectangle R. Okay, so then in each one of those subrectangles, we pick a sample point. Maybe it's the midpoint, maybe it's the upper left corner or the lower left or any other point inside each subrectangle. We can then form the Riemann sum, which is given by this sum of terms. It's a sum over all the subrectangles, and it's a sum of terms which are each the volume of a rectangular box. And here's a good picture, which I didn't show last time because I had to look around in a few textbooks to find it. But here's a good picture for what the Riemann sum represents. It's a sum of the volumes of a bunch of boxes like this one. And altogether, they approximate the true volume underneath the curve, or underneath the surface. Finally, then we could define the double integral of f of the limit of those Riemann sums as the number of subrectangles goes to infinity. And in that limit, we'll get the actual true volume beneath the graph. So it's a bit beyond, well, it's far beyond the scope of this class to truly justify that this is an equivalent definition, although some textbooks will actually take this as the definition of volume. If you think about it, volume is not so obvious a concept to define. Like if you really think about it, what's the volume of this lectern? Well, it looks like it's made up of geometric shapes, but if you could get in there with a magnifying glass, you'd see that actually this is mostly empty space in between atoms. I mean, like the distance from the nucleus of an atom to the electrons orbiting it is far greater, at least in ratio, than the sun is to Pluto. So there's mostly empty space in what looks like a solid volume. So volume is not so easy to really define when you really think about it. It's an interesting concept, which is the subject of a field of math known as measure theory, which I actually know a bit about because I used it in my dissertation. So it's a pretty cool topic. I won't say more about it here and now, but I will now do an example of Riemann sums. So let's approximate the volume beneath. You choose a function here. I guess you choose a function here. Can someone choose a function here? A function of two variables that we can do a Riemann sum with? You have an idea? 2x y squared. Ooh, 2x y. I can do that one. No, I know why you said that. Okay, we'll do 2x y squared. And we'll do it on, I had to pick some rectangle. Let's do the unit square, 0, 1 cross 0, 1. Just keep things easy. I could do it on any other rectangle, though. And let's use 4 subrectangles. And let's choose the midpoint of each subrectangle for the sample points. So let me draw a picture of that. Let's say that this is the xy plane. And let's say this is now the rectangle 0, 1 cross 0, 1. And I'm going to split it into 4 subrectangles by splitting it in half in the x direction and also in the y direction. So apparently I split it at 0.5 in the x and also 0.5 in the y. I now have 4 subrectangles, and I'm going to choose the midpoint of each for my sample point. So the midpoint of this subrectangle is where the x-coordinate is the midpoint of 0 and 0.5, which is 0.25. The y-coordinate actually is also the midpoint of 0 and 0.5, which is also 0.25. So my first sample point will be 0.25, 0.25. Let's see, next, the y-coordinate will be the same right here, but the x-coordinate will be the midpoint of 0.5 and 1, which is 0.75. So my second sample point will be 0.75, 0.25. Let's see. For the upper left subrectangle, the x-coordinate will again be 0.25, but now the y-coordinate will be 0.75 because that's the midpoint of 0.5 and 1. And then my last sample point will be the midpoint of the subrectangle in the upper right, which, as we can see, has x and y coordinates both being 0.75. Okay. Now I just need to evaluate the function at those 4 points and multiply, by the area of each subrectangle. So let's see. The height of each subrectangle is 0.5. The width of each subrectangle is also 0.5. So the area of each subrectangle is 0.5 times 0.5, which is 0.25. So my Riemann sum will be, let's see, it'll be f at the first sample point times 0.25 plus f at the second sample point times 0.25 plus f at the third sample point, 0.75, 0.25 times 0.25 plus f at the last sample point. Times 0.25. And I'll plug this in on a calculator at this point. So let's define f of x, y. What did we say it was? 2x squared? Is that what we said? 2x squared y? Yeah, 2xy squared, sorry. 2xy squared. And then let's see, I'm going to, I can pull out the 0.25, by the way, of each term. So I'm just going to pull out that common factor of 0.25. So I'll have a 0.25 times, let's see, f of 0.25, 0.25 plus f of 0.25, 0.75 plus f of 0.75, 0.25 plus f of 0.75, 0.75. And there we get an answer. So 0.3125. Now, this should be an approximation to the volume beneath the graph. If you want to see what that volume looks like, I can bring it up real fast. Give me a second to bring up Math 3D. There. So 2xy squared on 0, 1 cross 0, 1. Hey. Oh, oops. There we go. Cool. So we just found the volume beneath this cute little function. Oh, look at that. So, yes, you're right. Thank you. Yes, we have found an approximation to the volume beneath this cute little thing. So we found an approximation to this region right here, this solid region underneath the function. It's approximately 0.3125. Okay, any questions? All right. So Riemann sums are super useful in application. But we're going to focus on a more theoretical technique for computing double integrals. For our purposes now, for the most part, we're going to use the method of iterated integrals for computing double integrals. So this is going to make use of Math 10b material. It makes a comeback now, finally, after all this time. So let me start talking about iterated integrals. What are they? What are they good for? For starters, let me make a definition clear. This is kind of going to be the inverse operation of taking a partial derivative. So suppose we have a function of two variables, f of x and y. If I write down the definite integral symbol, that is an integral sign with a subscript and a superscript for the lower and upper limits, of f of xy dx, that means you just take the familiar one variable definite integral of this expression from a to b, and you treat y as a constant. All right, whatever it is, it's just some constant, just leave it as y. So that's fine. Your answer will, in general, depend on y. Remember when you learned about antiderivatives, which is like the inverse operation of taking a derivative? Well, this is kind of like an anti-partial derivative. Now, that's not an official term. I wouldn't go around calling it an anti-partial derivative. Well, I guess you could, but I made that word up, so no one but me will be impressed if you do that. But let me show you an example. How about the integral from 6 to 9 of y squared over x dx? So the dx symbol here is important. It tells you what you are integrating with respect to, which means you should hold everything else fixed. So in this case, we'll hold the y squared fixed, which means we could pull the y squared out in front because it's like a constant. So this will equal y squared times the integral from 6 to 9 of 1 over x. And if you remember from all the way back in the Math 10b class of yesteryear, what the integral of 1 over x is, it's ln of x. So this will be ln, technically of absolute value x, from 6 to 9. Oh, and I put here this evaluation bar. Sometimes when we have multiple variables involved, I like to write exactly what it is we are evaluating from 6 to 9, just so there's no chance of confusion. It's x that we are evaluating from 6 to 9. Sometimes I'll even put an x equals 9 at the top just because it looks prettier. Sometimes I don't, though. In either case, let's evaluate this from x equals 6 to x equals 9. That will give us y squared times ln 6, no, ln 9 minus ln 6. Now, OK, cool. So that's that. Now, similarly, we could define the integral, say, from c to d of f of xy dy. If I put a dy there, that indicates that you hold x fixed and integrate with respect to y. If I did that, for example, let's say, just to show you what I'm talking about, if I did 6 over 9 y squared over x dy, that would mean we hold x fixed. And we would integrate that 1 over x factor times the integral of y squared dy, which would be 1 over x times 1/3 y cubed evaluated from y equals 6 to 9, which would be 1/3 of what? 9 cubed minus 6 cubed, all over x. If you think about it, these two types of definite integrals give you the area of a cross-section of the solid underneath the graph of f. So suppose, here, look at this picture, and suppose this surface right here on top, that's the graph of z equals f. Now, if you fix an x value and integrate, if you fix an x value, then you get a function which depends on y. And we already know from Math 10b that when you integrate a function, you get the area under that curve. So that will give you this area. This area would be the integral from c to d of f of x, y, dy. Similarly, you could fix y. That gives you some function which only depends on x. And the integral would give you the area underneath that curve, namely this one. So that would be the integral from a to b of f of x, y, dx. So what does this have to do with double integrals? Well, there's a famous theorem about how these concepts relate to double integrals. It's called Fubini's theorem. I know Fubini's theorem quite well because I actually used it in a few important ways on my dissertation. So yeah, I spent a lot of time studying Fubini's theorem. It turns out, by the way, to have a much more general version than the one that I'm showing you here now. But here's what it says. Suppose that f is a continuous function defined on some rectangle R equals AB cross CD. Then the double integral of f over R is equal to the following. We integrate f from c to d with respect to y, holding x fixed, as I just explained. That gives you something that depends on x, right? Kind of like in the last example. The answer here was a function of x, so you can integrate that with respect to x. And if you integrate that from the x limits of a to b, you get the double integral of f. So that's kind of crazy. You can do this iterated single one variable integral, and out pops the value of the volume underneath the graph. And moreover, you could also do it in the reverse order. You could have integrated f with respect to x from a to b. That gives you some expression which depends on y, and you then integrate that from c to d with respect to y. So these two expressions are what we mean by iterated integrals. Iterated means one after the other. So Fubini's theorem, it's actually a pretty deep statement. It contains a lot. There's actually two main takeaways, or two important results of Fubini's theorem. For one, it states that you can find a double integral by taking two iterated one variable integrals. So that's a deep and non-trivial statement unto itself. Moreover, it states that it doesn't matter in which order you perform the iterated integration. That's also a deep and non-trivial statement. So I really should have brought like a loaf of bread into class today. Maybe I can use this eraser. What Fubini's theorem says is, if I imagine this is a loaf of bread, and I chop it into a bunch of slices in the familiar way. If I add up the volume of each of those slices, I get the volume of the whole loaf. Moreover, I could do the same thing in the psychopathic and long way of slicing the bread. And I could still, even though this would be, like I said, a psychopathic way to slice a loaf of bread, I could still slice it into a bunch of slices like this way and add up the volumes of the slices and get the volume of the whole loaf. So, as a consequence of Fubini's theorem, you now know that you can choose which order you want to integrate in. And you are free to change the order of integration. But if and when you do, make sure you remember to also change the limits. Right? Notice that when you do the x integral first, it's the x limits that come first. And by default, if you're given an interval, you usually assume, unless you have information to the contrary, that x is in the first and y is in the second interval. X comes from the first interval and y comes from the second interval. Also, there's a new notation which we commonly use. We often drop the parentheses in an iterated integral. So we're often not going to write them, and it will be up to you to insert them in your mind. What that means is when you see some iterated integral, a, b, c to d, f, let's say dy dx, the dy dx should be read from the inside out and not from left to right. Because if you read it left to right, actually, wait. Well, okay, I guess you kind of do read it left to right. So it's the integral signs, which you should not read left to right. You read the integrals from the inside out. Okay, let me say that. That makes it a bit more clear. Read the integrals from the inside out. So when you see this, the CD goes with the dy integral, and that's the one that you do first. You insert these parentheses in your mind. And then whatever you get from that, you then do the AB integral with respect to x. So let's try practicing that. Is it true that the iterated integral from a to b with respect to x of the integral from c to d of f of xy with respect to y is equal to the integral from a to b, the integral from c to d, f of xy dx dy. Is that a true equality? Say 1 for yes or 2 for no. Oh, good. All right, yes, I'm seeing mostly no's. So yeah, I got that one wrong. If you insert parentheses in your mind, you can see that I failed to switch up the limits of integration right there. Like, I could do the dx integral first, but I should also change the limits to be, well, the x limits, which went from a to b. Okay, so here, let me do an example. How about the double integral over 6/9 cross 1/2 of y squared over x. So this will equal the integral. Let's see, it doesn't really matter which one we do first. What should we do here? I'll do the 6 to 9 part first, because I actually already did that integral. So I'll first do dx, and then I'll do 1 to 2 of that dy. So this will equal the integral from 1 to 2 dy of an answer I actually already calculated, which was, what was it? It was y squared ln 9 minus ln 6. And that integral, the ln 9 minus ln 6 part can actually be pulled in front as a constant. And I'm left with the integral of y squared which is 1/3 y cubed evaluated from y equals 1 to 2 which is 1/3 of 2 cubed minus 1 cubed, which is 7/3. Okay. So, any questions? Yeah, Brian? So, it was actually up to you which one you wanted to do first. So I could have gotten the same answer if I had integrated with respect to y first. Now, are you asking how did I know that these were the x limits?
Yes.
Yeah, that's a good question. So technically, frankly, actually, that's a valid concern. And my answer to that is just by convention. So unless you're given information to the contrary, just assume that the first interval is the x interval. But yeah, that's a totally fair point, actually, technically. Okay, so now that we see that we can use 10b techniques to evaluate double integrals, I wrote up an entire course in one page. So this is all of 10b, which I actually taught last winter. That's why I still had all these equations already written up. Yeah, in one page. So you may recall that you learned antiderivatives, which is just another word for indefinite integral. Right? Antiderivative and indefinite integral are two words that mean the same thing. And this is what they were. In particular, I want to point out the power rule, which is probably the most commonly used one. Of course, you should also know what the antiderivative of cosine is and sine. And these linearity properties are important as well. You use them a lot. And once you know antiderivatives, you can evaluate definite integrals by way of the fundamental theorem of calculus, which says that if you know what the indefinite integral is, then you can compute the definite integral by just evaluating the function at the two endpoints and subtracting the value at the lower endpoint from the value at the upper endpoint. I also reminded you of a couple of rules like the substitution and integration by parts rule, and I tossed the average formula on here, not because we're going to use it, but because I'm going to show you the two-dimensional average formula, which you can contrast with the one variable average formula. Let's see. So there's some examples in the book that I'm not going to have time to do. Most of them, actually, you'll have to read. I'll show you one where choosing the order of integration makes a difference. So let's say we want to integrate x over y squared plus 1 to the 3/2 power over the square -1, 1 cross -1, 1. So which variable should we integrate with respect to first? There's an easy one to do first and a hard one. In fact, I don't even know what the other one is, not off the top of my head. Which one should I put on the inside? Yeah, let's do x first. That looks way easier. So doing the x integral first, the y squared plus 1 to 3/2 is like a constant. We can actually pull it out in front. It's like some constant factor. So it's actually this factor, whatever the heck it is, I don't even know what that integral is, times the integral from -1 to 1 of x dx. Well, what the heck is that? Here, this is 1/2 x squared evaluated from x equals -1 to 1, which is 1/2 of 1 squared minus 1 squared, which is 0. So I get a factor of 0. I don't even have to evaluate the y integral. I'm already done, because I got a factor of 0, so the whole thing is 0. Like, whatever the y integral is, it's being multiplied by 0, so I already know what the answer is going to be. So that's one example of using your noggin to figure out how to do a problem in an easier way. Another example of that would be the next example, which I'm not going to have time to do right now, but it's actually in the book, so you should definitely read example 5.7. And in fact, there's a bunch of other examples you should read that make use of the following double integral properties. So let me start telling you about the properties. There's a bunch of properties here. Most of them will look familiar. Most of them are just what you would hope is true. All but the last one. So these first 4 are all also going to apply once we learn about integrals over more general regions in section 5.2. I almost didn't even want to show them to you now, because I'm going to have to mention them in 5.2 as well, because they also hold in that context. So here's what these properties are. And like I said, these first 4 also work for regions more general than rectangles. So they state that if you integrate a sum of 2 functions over some region, that's the same as the sum of the 2 double integrals of the 2 functions over that region. So that's nice. You can interchange an integral and a summation sign. Similarly, this is the other linearity, so-called linearity property. If you have a constant factor in front of a function, you can pull that in front of a double integral. Another property is, let's say you want to integrate over a union of 2 rectangles. Say like this. If you split R into 2 rectangles, S and T, the integral of f over R is the sum of the integral over S and the integral over T. And this property also holds for much more general shaped regions. I'm showing it to you now for rectangles, but it actually holds for any non-overlapping regions S and T. Fourth property states that if you integrate the function 1 over a region, you get the area of the region. So this is kind of interesting. This is a new area formula. Now, as presented right here, it's not particularly interesting because it's just for the area of a rectangle, but it's going to be shown to hold in section 5.2 for much more general shaped regions. Finally, we have a property that is only for rectangles. So this is the only one that's only for rectangles. And it's a shortcut, really. It's a shortcut for evaluating double integrals of functions that are a product of a function of x and a function of y. It's actually making use of what I've already been doing in my examples, where I would pull the factor of x or y out in front. So it states that the double integral over a rectangle of this product of x, of this product of a function of x with a function of y can be evaluated as the product of 2 single integrals. The first one of the function of x and the second of the function of y, according to their respective bounds. So I was actually using this property, or I was using how you would prove this property in like the last example where I pulled the factor out in front of the integral. I was basically using that shortcut right there. Okay, let's see. So yeah, I just said this. There's some examples in the book, like 5.3, 5.4, 5.5, and 5.6, which show you examples of the use of these properties. And I'm not going to have time to cover them all, but you should totally read them because they're important. I just don't have time to cover them in lecture. What I want to show you is another application, an important application of double integrals. So I already mentioned the area property. I mentioned it like a minute ago. So I said that if you integrate the function 1 over a region, you just get the area of the region. For now, this holds true for rectangles, but next section we're going to show it actually holds true for any region. Okay, yeah, that's what I was saying right here. So this will be really important in 5.2. But at least right now, we have another use for this formula. We can define an average formula. This is actually one of my favorite applications of calculus. I love questions about averages. I almost certainly will ask some test question about average. They incorporate multiple concepts all at once, and there's a lot of physical intuition in them. So we can define the average of a function of two variables, f of x, y, to be the following. So it's some number, I'll call it f sub AVE, and it's equal to the double integral of f over its domain divided by the area of that domain. Contrast this, by the way, with the one variable definition, which I wrote a little bit ago in my 10b reference. It was 1 over b minus a times the integral from a to b of f of x dx. That was your one variable average formula. Here's your function of two variable average formula. In both cases, you integrate over the domain and divide by the measure of that domain, be that length or area. So let's try an example. Wow, I'm going to finish today. Hell yeah. Way farther in this class than I did in A00. God, I must spend too much time screwing around just blathering A00. So let's apply this example. I said an example 2. I think any example where we have an answer would work. Oops. In example 2, I think we did that. Oh, yeah. So example 2, in example 2, we did 6 to 9, 1 to 2, y squared over x, and we got it to be that. So find the average of y squared over x on the rectangle 6, 9 cross 1, 2. So the answer, well, it'll be 1 over the area of that rectangle, the area of whatever that rectangle is. It was 6, 9 cross 1, 2. Times the double integral over 6, 9 cross 1, 2 of y squared over x dA. So we already computed the double integral part, or this part anyway. It was 7/3 ln 9 minus ln 6. Oh, by the way, ln 9 minus ln 6, Yes or no? Is that equal to ln of 3/2? Yes, yes it is. I think I'm going to put a log property part of in one of your written homework problems, by the way. So if you know that this is true, then you'll be in good shape for that. Yes, that's true. That's from log properties. So what's the answer to this average then? Well, I guess I'm going to need the area of this rectangle. What's the area of the rectangle? The area of this rectangle, well, let's see. I can draw the rectangle. It goes from 6 to 9 and from 1 to 2. So it's a 3 by 1 rectangle. So the area is 3. Good. Yes, the area is 3. So the answer will be 1/3 of 7/3 times ln 9 minus ln 6, or if I simplify that using log properties, 7/9 times ln of 3/2. Cool. Ow. 149. Nice. Yes? Oh, yeah, indeed. So here's a log property for you. Ln of A minus ln of B is ln of A over B. So yeah, I did 9/6, and then I canceled it to 3/2. Mm-hmm. Cool. All right, right on time. In fact, early. So have a nice Thanksgiving break, folks. See y'all week 10.